Imagine a light switch with a simple job. Every time you press it, the light changes. On becomes off, and off becomes on. In classical computers, this is called a NOT operation. It simply flips a 0 into a 1 and a 1 into a 0. Quantum computers perform the same idea, using a gate known as the Pauli-X Gate. The Pauli-X Gate flips a qubit from the 0 state to the 1 state, and from 1 back to 0. Mathematically, the Pauli-X Gate swaps the two basis states. It is the quantum version of the familiar NOT gate. Even when a qubit exists in a superposition, the Pauli-X Gate flips its amplitudes while preserving the rules of quantum mechanics.
Although simple, the Pauli-X Gate is one of the fundamental building blocks used in larger quantum circuits.
Every powerful quantum computation begins with simple operations. Sometimes, changing everything starts with a single flip.
Alone, the Pauli-X Gate is simple. Combined with other gates, it becomes part of the language that quantum computers use to solve extraordinary problems.
In quantum computing, even the simplest gate can unlock remarkable possibilities. The Pauli-X Gate reminds us that every great quantum journey begins with a single, perfect flip.
Like a single brick in a skyscraper, the Pauli-X Gate may seem simple, yet countless quantum algorithms rely on this fundamental operation as one of their first building blocks. Real quantum computers are incredibly fragile. The Pauli-X Gate also plays an essential role in quantum error correction. It helps recover information when noise threatens to destroy it. The Pauli-X Gate doesn't perform the most complicated quantum operation, but by simply turning of every quantum computer's language. On the Bloch sphere, the Pauli-X Gate is a perfect 180-degree rotation around the x-axis. The Pauli-X Gate does more than flip a state. It prepares qubits for complex quantum operations that power tomorrow's algorithms. Every time our student presses the switch, he is unknowingly performing the same operation that quantum computers perform. One state changes into another. Simple, reversible, powerful. The next time you turn on a light, remember, somewhere inside a quantum computer, a tiny qubit is doing exactly the same thing. Physicists simply call it the Pauli-X Gate.
Imagine owning a compass that doesn't simply point north or south. Until you look at it, it somehow points in both directions at the same time.
Physicists often visualize a qubit using a Bloch sphere. The North Pole represents the state 0, while the South Pole represents the state 1. Quantum gates don't simply switch values. Instead, they rotate the state of a qubit around different axes of this sphere. Among the most important quantum operations are the Pauli gates, X, Y, and Z. Each transforms a qubit in its own unique way. The Pauli-X Gate behaves much like a classical NOT gate. It flips a qubit from 0 to 1, and from 1 back to 0. But the Pauli-Y Gate is far more interesting. It doesn't merely flip a qubit, it also changes its quantum phase.
Mathematically, the Pauli-Y Gate performs a 180-degree rotation around the y-axis of the Bloch sphere.
This is the difference between ordinary computers and quantum computers. Applying the Pauli-Y Gate transforms the 0 state into I times 1, and the 1 state into negative I times 0. These imaginary factors are known as quantum phases. Quantum phases may seem invisible, but they determine how probability waves interfere with one another. They are essential for the extraordinary power of quantum algorithms. Unlike the Pauli-X Gate, which only changes the state, the Pauli-Y Gate changes both the state and its phase, making it uniquely useful in quantum computations. Today's quantum processors implement Pauli gates as fundamental building blocks for controlling qubits with incredible precision. The Pauli-Y Gate plays an important role in quantum simulations, error correction techniques, and powerful quantum algorithms. That mysterious compass was never broken. It was behaving like a qubit experiencing a Pauli-Y transformation, changing direction while also acquiring a hidden quantum twist. The Pauli-Y gate reminds us that in the quantum world, information isn't just about zeros and ones. Sometimes, the most important changes happen in dimensions we cannot directly see.